This is another edition of ScoreBooster chemistry project, and our topic for today is going to be on electricity and chemical change. And our regular presenter is going to be Latif. When we say electricity and chemical change, what do we really mean by that? During the start of this class, of this course, we talked about physical and chemical change. We said physical changes are those ones that can easily be reversed upon which no new substances are formed. The opposite is that of chemical change, in that there are formation of new substances. A great deal of it is involved, and it involves chemical reaction. So during the course of this subject, we have been encountering many reactions, both physical and chemical reactions. Even in the last lecture, when we talked about oxidation reduction reaction, we still said that was part of chemical reaction. So today now, we want to see the effect of electricity on chemical change. How can electricity cause chemical change? Because you say when we have chemical reactions, there are many things that can be used to facilitate reactions. We talk about temperature, we talk about light intensity, surface area, and all whatnot. They are not limited to that. So electricity is also part of it, but in this case, it is not going to be a case of you are trying to react a substance A and B together from substance C and D. The application of electricity to cause chemical change is on a new dimension in this topic. Somebody will ask why we are treating it. Yes, it is important that we treat, as we are going to see later. This has applications in various industries: steel and wires industry, wire and cables, extraction industries, manufacturing, even electrical industries. We are going to see how these ideas, how these concepts are being employed in all the industries I've mentioned. But before we go, let us try to look at our learning objectives. We are expected to be able to distinguish between what is called electrolyte and non-electrolyte. And we should be able to give examples. We should identify reactions occurring at the electrodes and the product at each of the electrodes. Because it is important, it's only when we identify the reactions that are occurring at each of the electrodes. Of course, we know what is called electrode before we will be able to identify the reactions occurring at each of the electrodes, then the product that is being produced. Perform electrolysis of some compounds, then perform simple calculation based on Faraday's laws, and specify the areas of application of electrolysis. Those are the main components of our discussion for today. Let us sit back and see how we are going to take them one after the other. The setup we see here consists of a battery. This is a battery. This is wires. This is a rod. This is a bulb. So schematically, this is what we have here. What we have here is the same as what is happening. This is our battery. This is the wire, this is the bulb, this is the carbon rod, this is. So we are using carbon rod because it is not just carbon like that, is graphite. Graphite is an allotrope of carbon. So this one has some free electrons that can allow passage of electricity. So when this cell is closed, when all the wires are connected together like that, the bulb will light up. Why? The bulb lights up because there is passage of electron from the negative terminal of the battery towards the bulb through the carbon rod and back to the positive terminal like that. This flow of electron, the flow of the streams of electron that constitute what is called electric current. That electric current is what hits the filament of the bulb, and the bulb is lit. So we see light on the bulb. That is what is happening in the bulb. In other words, the flow of electricity or current of electron is what brings electricity, is what brings the light. The light, I mean. The flow of electrons inside the battery, inside the wire, is what is called electricity, electric current flow. So what makes electron to flow? It is because in the battery here we have the balance of negative and positive ions inside the battery. So we have two terminals here. One is where an electron will leave the battery, then the other one is where the electron will enter the battery. So there is going to be balance at every point in time when the circuit is closed. When the circuit is open, I mean in this case now, if we don't have any of the terminal, let's say we don't have wire here now, so we just leave it free like this, and wire is free, that's an open circuit. Nothing will flow because there is no bridge that will bridge the source of the electron, then the other part of the circuit. So if we have a key here, let us assume we have a key here, and we connect everything together, we leave the key open. If we leave the key open, current will still not flow because the circuit is not connected together. So when the key is now closed, then the current will flow. That is, the current flow because there is going to be a balance of electron in that it enters somewhere and exits in another place. In the circuit that we just saw above now, the copper rod that we used, we said it has free electrons that can allow the current to pass through it. If assume that we use another substance, let's say a paper, to connect this place to this place, is there going to be any current flow? That is what we need to ask ourselves. If there is not going to be current flow, then what do we call it? If there is going to be current flow, what do we call it? That brings us to the concept of conductors and insulators. So in the circuit above, the graphite and copper that allow electricity to pass through them are called conductors. They allow electrons to pass. And don't forget, we have defined electricity to be the passage of electrons. Anything that allows electrons to pass through it, they are called conductors. Because when electrons pass through it, that is when you see light. But if a piece of plastic or ceramic is connected to the circuit, the bulb will not flow. Why? Because the plastic or ceramic do not contain free electrons that constitute what is called electricity flow. In that case, any substance that disallows the passage of current, the passage of electrons, into itself or through itself are called insulators. Examples are plastic, that we have said, ceramic, paper, clothes, like that. There are many examples of conductors. We have the metals like iron, like steel, like copper, non-metal also, like a graphite now, that's an example of a carbon that conducts electricity. Not every allotropes of carbon conduct electricity. Graphite is an example of one that conducts because it has free electrons around its structure. So these are solid. There are some times that we have liquid that conduct. We are going to see that later. But let us finish on this conductors and insulator first. Somebody will ask why we are concerned ourselves with insulators. Yes, it's a very good question. It is not every time that we need something to conduct electricity for us. And as I've said earlier, if we leave this terminal open, nothing will flow. But if it's now connected like this, electricity flows. What of if someone now put his hand here or anywhere on where unprotected? What will happen to the person? The electron will flow through the person and the person gets shocked. That's what is called electric shock. And if the voltage is very high, we have what is called electrocution. In fact, sometimes it can be fatal. So in that case, in all the appliances, or let me say majority of appliances that we use at home that uses electricity, there is possibility of having electric shock when naked wires are touched. We have stabilizers, we have our radios, we have our televisions, clippers, almost everything that uses electricity. It is not safe to touch them with bare hands like that unless there is a protective substance. Then what can we use as a protective substance? It is something that disallows the passage of current. That is why insulators are useful. So in the case now that we want to barb our hair now, we have a clipper that uses electricity. We need to hold the clipper somewhere so that it is easy for us to barb our hair, to cut our hair. So that place where we are holding the clipper is made of plastic. So because plastic is insulator, it serves that purpose. Another one is the cables of electricity that pass through everywhere. They are conductors, because we want them to pass electricity. So we need something that allows passage of electrons. So aluminium is a very good conductor, steel is a very good conductor, copper is a very good conductor. In fact, gold is a very good conductor of electricity. Another one is when we have, everybody knows high tension cables that runs across main roads. On these high tension cables, the voltage that has been carried are very enormous, that if any living thing just go close to it or just mistakenly touch it, under 1 millisecond the person is died or the thing is dead. So in order to prevent such occurrence, and to safeguard people that are working with electricity companies. Some ceramic discs are used to support the wires, that that point where the wire is passing over that pole, all those poles, you see ceramic there. That ceramic is because it disallows the passage of current. So if there's no ceramic there, electrons that are just passing on the wire will just go down through the pole to the ground, and people will get electric shocks all around. In order to forestall that, ceramics are used to prevent that current from escaping. This is because ceramic is an insulator. That is application of insulator. Another one is all the wires, everything that we use at home or industry that has wires. There is a plastic that is melt around it, so that the wire just pass through those plastics or rubbers to prevent shock and electrocution. So those substances that are used to protect the wires are insulators. The plug cases are made of plastic also. Those are the uses of conductors and insulators. If we have a liquid, can we call them conductor? As we all know, chemistry is the science of substances. We have talked about different sets of substances. We talk about solid and liquid. So we have settled that of solid, insulators and conductors. What about that of liquid? Is it possible for liquid to conduct electricity? If yes, what is the driver? Like we have electrons in the solid. In the liquid, what we have, if at all liquid conduct electricity? Just let us try to see. As I've said earlier, the copper wires that we saw and the graphite in those circuits above, in the circuit above, were able to conduct electricity because of the free electrons in them. So any substance that has free electrons will conduct electricity. Free mobile electrons conduct electricity. What about the molecular compounds? The molecules, they are insulators because they do not have free electrons. I've said earlier on, that one is just to buttress that point. Ionic compounds, they are not molecular in this case. They are ionic. They are able to conduct electricity, but not at that state where they are. They have to be converted, to be transformed into another state, so as to make them able to conduct current. Example is iron sulfate, copper sulfate, sodium chloride, magnesium chloride, magnesium nitrate, sodium nitrate, nickel nitrate, nickel sulfate, mercury chloride. All those ionic compounds, in their solid state, they do not conduct electricity because they don't have free electrons, they don't have free ions. So if you want them to conduct electricity, then we have to dissociate them into their constituent ions. After they are dissociated, then the ions will now be the agents of electricity, as we have electrons in the solid. So in these compounds now, they are in molten state, so they are not liquid again, they are not solid, they are in molten state. Then the ions are set free, then their currents are allowed to pass. So if you ask what is the carrier of electricity in ionic compounds in molten state, they are called ions. In solids are called electrons. Even in liquids, they are called ions, because apart from these substances turned into a molten state, we can turn them into solution that just pour water into it. The soluble ones, the soluble ones. So when the water is being poured into them, we are going to dissociation into separate ions. Those ions will be able to conduct electricity. That is what we are saying. So if you want to dissociate them, there are many ways to dissociate them. I have talked about use of water. So another one is the use of electricity. If there is a passage of electric current through them, then they dissociate. When they dissociate, that is called electrolysis. Electrolysis is from the word electro, means electricity. Lysis is to break something. If you break something with the help of electricity, it's called electrolysis. So the liquid that conducts electricity is called electrolyte. Although we have some strong electrolytes and weak electrolytes, like we said in acid, when we have strong acid and weak acid, the level of dissociation in acid tells us if it is strong or weak. So the same thing in this electrolyte, the level of dissociation, the ease at which it dissociates, tells us the nature of the electrolyte. If it's readily dissociates, then we have strong electrolyte. If it's sparingly dissociated, that is called weak electrolyte. Then, do we just pass electric current into it like that? Of course, no. There are some substances that are deep inside those ionic compounds before the current are passed through them. Those substances allow electricity to pass through them, and they cause dissociation of ionic compounds. They are called electrodes. Electrodes are rods that allows electricity to pass through them, thereby causing dissociation in the ionic compounds, that is electrodes. Now, electricity, what is the principle of electricity? Electrolysis is the breaking down by electricity. So any liquid that contains ions will conduct electricity. So before I go to this, let me just give an example of what is called electrolyte and non-electrolyte. If we have a sugar that we take at home, you pour water into it and you pass electricity to it, or you have ethanol or dimethyl ether or methanol, you pass through, you make them in solution and you pass electrodes into them with current. What will happen? Is there going to be any conductance? No, they will not conduct, because they are all ionic and molecular compounds. They are covalent compounds. They will not conduct electricity because they are not dissociated at all into constituent ions. So, but sodium chloride, iron sulfate, copper sulfate that we talked about before, they will be able to conduct electricity in molten state and in solution, because they are ions, copper ions, sulfate ions. They are dissociated into all those ions. Then those ions pass. We allow electricity to pass because the agent of electricity in ions in solutions are called ions. So any liquid that contains ions will conduct electricity. So anyone that doesn't contain ion, so just ask yourself, just think like that and look at the examples of electrovalent compounds, then covalent compounds. Those covalent compounds, majority of them are non-electrolytes. So electrovalent compound, all of them are electrolytes, simply because they contain ions that are free to move when the compression to take place. So this is the setup of electrolytic cell. This is the switch I was talking about before. So although we have connected everything, this is our liquid, these are the electrodes. They are rods that are deep inside the solution to cause decomposition of this compound. So when this cell is closed now, NF, the wire joins, then the electron pass through here into the negative electrode. The decomposition takes place, electron pass through here like that and enter the other side of the battery. That is complete circuit. So the negative electrodes are called cathode. Negative electrodes are called cathode. Then the positive electrodes are called anode. Cathode, anode. Cathode is, let me just give you a tip to understand it. Cathode, cat, from cation. These electrodes love cation. So what are cations? Positively charged ions. So anything that love positive, they are negative, because unlike charges attract. Anything that attracts negative are positive, and vice versa. So far this one loves positive, they are negative. This one loves negative, they are positive. That is called cathode. Anode. Anode is from anion. From anion. That is just a tip to understand it. So now we said we want them to conduct, we want substance to conduct electricity in solution form or in molten form. If we have in solution form, it means we have added water to it. Then we have many ions inside, both positive and negative, depending on the nature of salt. If it's a simple salt and we add water to it, then we have positive ions 2, then 2 of negative ions. Then in electrolysis, we want to get the best out of the solution. We want to get some compounds out of the solution. How do we get them? What is going to be our guide on what the nature of electrode that we're going to select, or the nature of the salt that we're going to select? If we want substance A to be deposited, then what's our aim? How do we do it so that our intended substance is what we have after the electrolysis? The first thing that will guide us is the position of ions on the electrochemical series. There is a series like that that contains the list of positive ions and negative ions, the common ones, the ones whose salts are soluble, whose salts conduct electricity. Then this position is now something like the powerful ones belong to the top, then the weaker ones follow them. So if at any point we have 2 ions in the solution, one is stronger than the other, then the weaker one is discharged and the smaller ones remain in the solution, because the stronger one is strong, the weaker one gets discharged. Another one is the concentration. We are going to show us what is the electrochemical series later. Then the concentration of ions in the solution. I said concentration of ions. It depends, because it's relative time, it depends. If you have a salt solution now, you can define your concentration in terms of any of them. If it's a dilute solution of salt, it means there is more water than salt inside. Say there's concentrated something, it means there is that substance more than water inside. So now if you want to define it in terms of water inside, so if you have a much amount of water, that means there is high concentration of water. So don't let us go into that. So the ion with higher concentration are discharged, although this is just for ions that are close in the electrochemical series. So these are the points according to how important they are. Position of ions in the electrochemical series is the first point to consider if we want to know what elements are discharged. Then the concentration, then the nature of the electrode. The nature of the electrode is just when you don't have inert electrode. So if there is going to be any property of electrode that are similar to the properties of the ions concerned, then those ions get stick to each other because they love those electrodes. Like now, you have silver salt and you have silver electrolyte. So that means the silver will get discharged because his friend is the electrode. Like now, you have sodium salt and you have mercury electrode. Then they love each other. They form sodium mercury amalgam. That is the nature of the electrode. But if we have neutral electrode, inert electrode, these first 2 points are valid in determining which of them will get discharged. So this is what we are seeing in another words at the cathode, I mean the negative electrode. It is either you have the metal or the hydrogen that is formed, because we have said in solution now. So there is hydrogen from water, then there is positive ion from the salt. Number one, the more reactive an element, the more it likes to exist as ions. What I'm saying is this: if you have a metal that is above hydrogen in the electrochemical series, let's say sodium chloride now, you have sodium ions, then you have hydrogen ions. Sodium ion is higher than hydrogen ion in the electrochemical series. Then hydrogen is discharged because of the relative position in the electrochemical series. If you have calcium and hydrogen is discharged because calcium is far above hydrogen in the electrochemical series. That's what we are saying. But if the metal is less reactive than hydrogen, then the metal discharged, like copper now, like silver now. So hydrogen is more reactive than them. So when you have them, let's say copper salt, and we are using inert electrode, don't forget copper salt, like copper sulfate now, or silver nitrate. So the copper discharged or the silver discharged, then hydrogen is in the solution because hydrogen is higher than them on the electrochemical series. That's what we are saying. At the anode, that is the positive electrode, it's either you have the non-metal or you have the oxygen that is formed. Number one, if it is a concentrated solution of halide, like we have a compound, sodium chloride, sodium iodide, sodium bromide, potassium chloride, then the chloride forms. But if there is dilute solution now, then oxygen forms. This is the second point that we said, concentration now. If you have a dilute solution, then oxygen forms because the hydroxy from water is more than the chloride now. Then since the relative position on the electrochemical series is they are close, then the second point is now valid, that is concentration. The ion that has more concentration gets discharged. This is the electrochemical series that we said. This OH is not from sodium hydroxide, it's from water, because when there is decomposition of water, we have hydrogen ion and hydrogen ion. So now, if you have a solution of iodide, let's say zinc iodide now, if we have like that. So on the anode, we have this and this. This from the compound, this from the water. So if it's a concentrated one, then we have this discharged. If it's a dilute one, we have this one discharged because the position is just close to each other. Then this one are discharged because it has more concentration than this. So invariably that second point, that concentration of ions, is more applicable to these radicals, this negative aspect, the negative radicals, than this positive. In this positive ions, the position is clearly stated. It is either you have hydrogen and this, or you have this and this. It is only when you have something like a lead compound that point is not valid for this one. So even with that, hydrogen is still discharged. That is, if you are using silver electrode, a silver inert electrode. That is what we are saying. So now, let us now get the point and look at this table now to see if actually we understand the point. If we have concentration of potassium bromide, so I expect you to have written down the decomposition reaction and tells us the ions that are inside. So my own side here, I have hydrogen ion and hydrogen ion from water. Then I have potassium ion and bromide ion from this compound. So now, potassium and hydrogen goes to the cathode, bromide and OH go to the anode. So look at this. We have K on top, we have hydrogen here, then hydrogen is discharged at the cathode. We have bromine here and we have OH here. Then this is bromine, this is OH. What we're saying here, if it's a concentrated compound, then either of these get discharged, then bromine is at the anode discharged. So I think that one is clear. So let's go to dilute sodium chloride. The same thing applicable here. This is sodium, this is hydrogen. They are far from each other. The first point is the position of ions. So hydrogen is discharged. Then this is chlorine. This is this. So we go to this point. If there is dilute, the oxygen forms. This is oxygen that is formed. Oxygen is from here. So just write that reaction. This one loses electrons to the cathode and to the anode rather. Then there is going to be a evolution of water and oxygen. That is what we are seeing. So now, we have talked about oxidation and reduction reaction before. So how do we apply that electrolysis now into it? Because I said many of the reactions, if not all, many of the reactions are reduced. We have oxidation and reduction taking place together. So let us look at some examples and see if we can apply redox reaction to electrolysis. Number one, electrolysis of molten lead bromide. So molten lead bromide means there's no water inside. We just use electricity to decompose lead bromide into lead ions and bromide ions. So after the melting, we have the lead and the bromine. So the lead goes to the cathode, bromine goes to the anode. If lead goes to the cathode, what is cathode? Cathode is a negative electrode. That means there is electron around cathode, because that is where the electron is coming from the battery into the solution. So the lead accepts the electrons. After accepting the electron, then what did we call it that time? Gaining of electron. I remember we call it reduction reaction. When there is gain of electron, we have reduction reaction. And then you see lead around or at the bottom of that electrode, that cathode. So bromide ion move to the anode, then they lose electron because it is a diatomic molecule. It combined with another bromide ion, that is what I call double up. Then it bubbles off as a gas because it's a gas. So losing of electron by bromine to the anode is what is called oxidation. So overall, electrolysis is a redox reaction. Reduction takes place at the cathode, and oxidation takes place at the anode. That is what we are saying. So have you now seen why we learned redox reacting before electrolysis? That is science for you. Another example is the electrolysis of concentrated sodium chloride. Concentrated does not mean there's no water. There's water, but very limited, very little. The solution contains sodium and chlorine from this, then hydrogen and this from water. Then all those positive ions go to the cathode and negative ions go to the anode. Then at the cathode, hydrogen ions are discharged because of the relative position on the electrochemical series. What about the anode? We said if there is dilute, then oxygen form. If there is no dilute, then what form? The halogen forms. So chloride ion gives up the electrons, then they are discharged. So in the solution now, hydrogen ion has gone, chloride ion has gone, then we have sodium ion and hydrogen ion. So after the electrolysis, the only thing we have in the solution is sodium ion and hydrogen ion. Then when they react, they form sodium hydroxide. That sodium hydroxide is a very important chemical in industry, especially soap producing industries, detergent producing industries. You have seen why I said the compound you want to get determine how you want to set up your experiment. So it is our aim of getting sodium hydroxide here. That is where we are performing electrolysis on sodium chloride. Another one is electrolysis of dilute sodium chloride. The same ion are present as before, but in this case we have more water now than sodium chloride. So all those ion from water have higher concentration now in the solution than sodium and chloride ion. So at the cathode, same, hydrogen wins. Hydrogen is discharged because sodium is far above it. We can't even consider the concentration of hydrogen ion. So at the anode, since we have the negative ions that are close to each other, and we have hydrogen ion that have higher concentration, then oxygen is discharged. So invariably what we have at the end of the reaction, we have sodium ion and chloride ion. So as before, we still have our sodium chloride back. But what has happened? We have successfully dissociated water. That is just what happened. Our starting reaction is end reaction, but the concentration of sodium chloride will have increased because we have dissociated the water. That is just what happened. So when electrodes are not inert, that is our examples, the three examples that we have highlighted are when electrodes are inert. When they are not inert, what happens? The solution of copper sulfate contains blue copper 2 ions, sulfate ions, hydrogen ions, and hydrogen ions from water. Electrolysis of the solution will give different results depending on the electrode. So let us look at both cases, when we have inert electrodes and when we don't have inert electrodes. The first time when we have inert electrode, let's say carbon or platinum electrodes. At the cathode, if you are using carbon or platinum, I mean, at the cathode, copper are discharged because copper is below hydrogen. So copper ions are discharged. So when you have copper ions like that are discharged, copper ion coats the electrode because it gains electron from the cathode. So it's at the body of the cathode. So we have this copper at the body of the cathode, on the body of the cathode. So at the anode, oxygen bubbles off. Yes, because there's copper sulfate, so oxygen is discharged. Sulfate is far to oxygen. We can't consider the second point, the concentration. In this case, we consider the position of ions on the electrochemical series. So when they are far, it's only when they are close that we consider the concentration of ions. So the copper and oxygen are produced. What happens? The blue color of the solution fades because the copper ions that is responsible for the blue color has clinged onto the surface of the copper electrode. So as the reaction is going on, you are having more and more the amount of copper inside the solution keeps decreasing, so the solution fades. So there's going to be a time that we don't have copper again, then everything disappears. You don't have blue solution again. Only what we just have is the hydrogen inside and the solvent, and that is colorless. H2SO4 tetraosulfate 6 acid. That is when the electrodes are inert. When the electrodes are not inert, let us assume we are using copper electrodes. As the cathode, again copper is formed because copper gains electrode, so we don't have any problem with that. What about at the anode? We have copper anode, we have copper solution inside. Instead of another substance like OH or solvate to go to the anode, since we have natural affinity, copper and copper, they are more close, as in they are like each other. So the copper at the anode will lose the electron and goes into the solution as copper ions. These copper ions will then go to the electrode and form copper. So the same thing, anode again will be reducing in size as it is losing electron and go into the solution as copper ions. Then cathode will be increasing in size as it is gaining electrode and becoming copper atom. So the copper atom, the cathode will be increasing in size because more copper will be depositing on the surface of the cathode. Then the anode will be reducing. It is on this second point that the concept of application of electrolysis now enters: electroplating and purification of metals. Electroplating is when you use electricity to coat one metal with another to make it look better or to prevent corrosion. The handle of our bicycle and bikes are shiny because it was coated with chromium. But the chromium are not what we just coat on the surface of the steel material that was used to make the handles. We just coat it with nickel before to make the chromium to stay on heat. But the base material is steel. So what we are saying is there is electroplating. We have coated a steel material, we have coated with chromium. That is electroplating. Another one is you coat a steel jug with silver if you want it to look like silver. Yeah, they coat rings, they coat necklaces, they coat many things even with gold. So that is what we have. That is electroplating. If you want to coat anything with another substance, what you want to coat, the original material, in this case steel jug, you make it a cathode. Then what you want you to use to coat it, if you want to, like in silver now, you make silver the anode. Then you now use silver salt as the electrolyte. So as at the anode, the silver will be reducing in size as it is losing electron and going to the solution. Then the silver will be going towards the cathode. The silver ions will be going towards the cathode and gain electron there, then deposit itself on the surface of the steel jug. That's when you have silver color on top. If it is good like that, use a gold solution. If you want to coat, that is just the principle. If you want to coat A with B, use A as cathode, use B as anode, then you use a sort of B as the electrolyte. If any amplification of metal, if you have a metal extracted in the industry, that is the major use of electrolysis. It is applied in extraction industries, as I've said earlier on. You have metal extracted from the earth. Of course, it won't be neat. It will contain many substances. So when it contains many substances, we want to prefer it because there will be some element of sand, some element of other metals. If you want to get your metals, let's say gold, in 100%, what do you use? You get a gold, a clean gold. You make it a cathode. Then the impure gold that just extracted from the earth, you make it an anode. Then you look for a gold, a soluble salt of gold. You make it the electrolyte. So like we used to, I don't want to repeat the processes again. Just go to the anode. The anode that contains the impure substance will be going into the solution. When it loses electron, then when it's going to the pure solution as ions, the ions will be going towards the cathode and gaining the electrons. When it gains the electron, you see it on the surface of the cathode because it gains the electron and cling to it. So you replace the two electrodes. You put, as long as you have much good to purify. That is the application of those areas. Are two wide areas of application of electrolysis. So let us go into some calculations of electrolysis. So the major thing that we do in calculation on electrolysis is just Faraday's laws. We have two laws of Faraday. The first one is the amount of substances that is discharged. It depends on the current that is passed through it. What's the quantity of current that passed through it? Q is equal to IT. The amount of current and the time it's used to pass through it. That is the quantity of current. So if you want to get more substance during the electrolysis, you pass more current. That's what we are saying. I'm not saying you use more high. Say you pass more quantity, more Q. So you can increase your Q anyhow. Maybe you increase your I or you increase your T since Q is equal to IT. So the quantity of electricity is measured in Faraday, where 1 mole of electron is equal to 1 Faraday, and that is 96500 coulomb. So that is the first law we are going to see. The second law is when you have mixture of salts inside. Let's say you have copper sulfate, you have silver nitrate in the solution. You want them to be discharged. You use different electrodes. You pass the same current through them. So the mass of substances deposited are proportional to their respective chemical equivalent. What is chemical equivalent? Chemical equivalent is the molecular mass over the valency. So the molecular mass over the valency, if we look at that, we are going to see that the mass of substance deposited is inversely proportional to the valency. So like now, if you have a gram of copper deposited, since copper is a divalent metal, if you want to get what the same quantity that deposited 8 grams of copper, the quantity that quantity that will be deposited in silver is going to be double of that of copper, because silver is a monovalent element. And don't forget, the 1 mole of Faraday is equal to this. So 2 mole of Faraday is equal to this. So you have more quantity of electricity that will discharge more silver than copper. Don't forget this. You are going to use the two laws together. Just make sure you understand the two laws. That is what we have for today. So let us get over what we have talked about before we go to exercises. Electrolysis is the decomposition of salt by passage of electricity. The molecular compounds do not conduct electricity even when they are in solution. It is only the ionic compounds that conduct electricity in molten form or in solution. The position of ions on the electrochemical series, the concentration of ions, and the nature of the electrodes are some of the factors that affect discharge of ions. Then again, electrolysis are applied in electroplating, refining, and purification of metal. And lastly, Faraday is used to measure the quantity of electricity. With 1 Faraday is equal to 1 mole of electron and is equal to 96,500 coulombs of electricity. Which of the following happens during electrolysis of molten sodium chloride? When you have molten sodium chloride, what happens at the cathode? What happens at the anode? Just write down your ions that you expect. So you have sodium and chlorine. Sodium goes to the cathode, chlorine goes to the anode. What happens at the cathode? Reduction? Yes. Reduction happens at the cathode because sodium gains electron, chlorine loses electron. Just look at what we have. I've told you every options now. Just look at anyone that is aligned with what I've said. Sodium loses electrons? No. Chlorine gain electrons? No. Chlorine atom? No. Chloride ion gain electron? No. Sodium ion is oxidized? No. What is oxidation? Loss of electron. A and D are the same. They just want to confuse you. Chloride ion is oxidized. That is correct because it's chloride ion that go to the anode. Then oxidation takes place at the anode. That's what we are saying. A correct electrochemical series can be obtained from this by interchanging that. Although you are not expected to memorize this, but by constant practicing, you'll be able to know that magnesium comes before aluminium. Even if you don't know, just look at other options. Zinc and iron, I think they are not. Hydrogen and lead, they are correct like that. Gold and this, they are correct like that because gold is the last. Zinc and lead are correct like that. It is only the aluminium and magnesium that is, and that if you put magnesium first then aluminium, then there is going to be a correct order, although you are not expected to cram it. Once again, the mass of silver deposited when a current of 10 ampere is passed through a solution of silver salt for 30 seconds is dash. So don't forget our formula. Our M is proportional to Q. What is Q? IT. The mass of silver deposited when a current of 10 ampere passed through silver salt for 30 seconds. If you want to get your Q, multiply 10, multiply it by 30 seconds, you get 48,300 seconds. That's our Q. If 96,500, because silver is one monovalent element, so if 96,500, that is the coulomb that is being discharged by 1 Faraday. If 1 Faraday of electricity, that is equivalent to 1 mole of electron, is equal to 48,300. What is the mass of carbon? Of silver. So this 1 mole of silver that is discharged by 96,500 coulomb is equal to how much? I think 108 grams is equal to the mass of silver. So now 48,300 will now be how much? If 96,500 is equal to the mass of silver, then 48,300 will be equal to how much silver. So by my own calculation, I got option C, 13.5 grams, because Q is equal to IT. Then the number of mole is equal to Q over 2F. So if you have your Q 48,200, then you divide it by 2 Faraday. That is number of mole. If you multiply number of mole by 109, that is the molar mass of silver. You get option C. That is what I've said. So this is what we have for today, inshallah. So we are going to meet later on electrode potential. I believe you have understood everything that we discussed. If that is the case, don't forget to share and like our video. Thank you for listening, and God bless you really good.